Tonight, I'm not going to be teaching too long. Maybe about an hour should be fine, because we've covered the majority of the concepts. It's just adding on, adding on. So I'm just going to briefly review what we covered last week, just a general idea, and then going to take some questions from all of you. If you have any doubts, anything that I can clarify, and if you don't have, or if we can answer all your doubts and questions, then maybe I'll talk more about programmable logic, how to introduce the concept of programmability in digital design. And then we can end, if we are early, we can end early. If not, then it's fine. We just take as many questions as you have. No? Okay, so just hold your questions a little bit. Let me just give you a 5-10 minute review of what we covered the last 2 weeks, and then I can go ahead and take your questions now. So I think we were talking about this idea of digital systems design, right? And the key point is you are actually designing a digital circuit, okay? And before you even start designing, I had emphasized quite a lot. Before you start designing, please determine the specification of your system. And we talked about it in one full 2 hour plus session. What does that determine the specification of circuit mean? Well, you draw a black box, you draw a bunch of input signals, a bunch of output signals. You must label and name every input signal and every output signal. So you know what goes into your circuit, what comes out of it. And you must explain the encoding. What does a logic 1 mean? What does a logic 0 mean for input and output? And then you will define the sequence of inputs that you anticipate to receive, and the response of the circuit, which is also a sequence of output ones and zeros in response to a particular input pattern. And you have to do this as exhaustively and comprehensively as possible. You have to somehow find a way to document and explain this, okay? Because and normally you start by explaining what happens in the case that you want it to happen, like expected inputs. So these are the expected outputs. But you must also cover the case when the inputs are not expected. You don't expect it to happen, this kind of inputs, but if they do occur, what is the response of your circuit? Right, so that's the specification. And we talk beside the specification, the second thing you need to do is you have to think about, okay, this is a specification. How are you going to test? How are you going to verify that whatever you design meets this need? So this goes back to, you have to really define the test cases. That is the specific patterns of inputs that you are going to send into your circuit. And you have to describe what is the expected pattern of outputs for all and every single specific pattern. And we went through an example of that with this log example where, you were going through the specification, and as we started building the specification, we first did the cases that we knew these are expected inputs, but then we started building all the unexpected inputs. What happens if you do this? What happens if you do that? And you just get an idea that, wow, really you have to be very thorough in your specification. Otherwise, your circuit may have funny behavior that you don't anticipate, and it actually is not secure or it's not correct, right? So this is a matter about defining the correctness of the circuit. So then you figure out the test patterns, and it's not just enough to say, I'm going to test with something, right? You must actually say what is the patterns you are going to test. And here we talked about random samples, and then not just random samples, but changing number of samples, 4 buttons, 5 button sequence, 2 button sequence, and all that. So you have to specify what the system will do and specify how you will test the system. After you're done that, you are ready to design the circuit. Okay, and we talked about designing a hardware model, which is basically a description, a high-level description of what the circuit's supposed to do. I started by going through an algorithm, okay, because an algorithm is just a sequence of steps. But I also introduce you to this idea that the circuit basically has modes, and the modes are actually like different sort of calculations that you do on inputs. Okay, and the modes, I call them modes, but you are probably more familiar with the idea of state, right? So I'm saying mode because I just want you to not think about state at the moment, right? Because some people, when think about state, they have this very fixed idea that is just something out of the flip-flop. But a state is basically a mode. It's just a way for you to select which computational operation you're going to do, right? So you have a state machine, which is basically nothing else but a hardware encoding of a sequence of modes. That means your circuit is just going to go into mode 2 first, then mode 3, then mode 1, then mode 4, then mode 5. So that sequence of modes, which can be expressed as a state transition diagram. Because state transition diagram, each circle is a mode. And you have arrows that tell how you progress from one mode to another. Okay, and if there's nothing on those arrow means that every clock cycle, it just goes to the next mode, to the next mode. But usually what you have is you have certain conditions, input conditions that allow you to transition to that mode. And if you don't have that condition, you go into another mode, right? So a state machine is nothing else but saying, or explaining how are you progressing through the sequence of modes, and then you have to figure out what are the outputs at each mode. And that's actually the computation that you need to do. And when explaining this, we came to this idea that actually a state machine, you are still designing only combinational logic. You're not designing anything fancy, right? But what is a state exactly? It's just a bunch of flip-flops that memorize the mode. And there's some combination logic that will look at the current mode, that means the current state, and then we'll look at the inputs and decide what is the next mode. So I frame for you this idea of circuit design as basically a choice, represented by multiplexer. You can choose, depending on the mode, you can choose the calculation. And depending on the mode or the state, you can choose what is the next state depending on the inputs. Okay, and that's where we left off. That's the main point. And then I started kind of trying to persuade you that really a multiplexer can implement any digital logic, because a multiplexer can implement an AND gate, an OR gate, and a NOT gate. And you can implement any logic with combination of AND, OR, and NOT. Therefore, you can implement any logic with just multiplexers. And the multiplexer is kind of interesting because it's sort of a very natural way to think about if and else or case statements, right? Then the if and else condition is the C, the selector here, and then you're setting some kind of output based on the condition. So it maps very nicely. You can look at the circuit and straight away write Verilog code with your eyes kind of closed. Right, so that's the interesting idea about using a multiplexer to describe circuits. And you know that you can always convert this multiplexer representation of a digital logic into an AND or NOR gates, no problem, right? The synthesis tool could do that. Otherwise, you can just kind of implement a multiplexer as AND or NOR gates, and these become AND or NOR gates, and then you can go and do your Boolean optimization to reduce the number of gates. No problem. You know how to interconnect that. The other concept that we briefly talked about is this idea that beyond a multiplexer, okay, beyond a multiplexer, I can also implement any combinational logic using a memory element, where we were talking about a combination logic is nothing else but a bunch of input signals. Every sequence, every possible combination of bits in the input signal there will be described what is the output signal. So that's the truth table. And if you consider the input signal as the address to the memory, the data is actually the output. So you can literally just program the entire truth table into a memory. And this memory actually now becomes your combinational circuit. Okay, so this was the new concept that we talked about. Okay, I'm going to take a pause at this moment and ask you, do you have any trouble with what we've covered so far? Do you have anything that you don't understand about the textbook, the true textbook? Remember, my lectures are not going to be enough, because what I'm doing is I'm just supplementing, giving you insights, but you are supposed to read the true textbook to follow the examples there. You're supposed to also do a bit of extra reading on the Delhi textbook, and just pick this material up because there's plenty of examples there. Do some work examples. So if you have any difficulty, any concepts you'd like me to go over, this is a good time to ask. Please ask me and let me help to clarify it. Yeah. Okay, so nobody has typed anything or spoken up. So I will assume that that you're all okay with the concepts. You've had some time to look at it, but it's okay. If this was a busy week, you hadn't had time to think very deeply about it, please go over it this week or next week. And if you have questions, you know how to reach me. WhatsApp. You can post it in ULearn, or we can talk about it in the next session. I want to take today's session a little further. It's not going to be a very long session. I hope we can wrap things up within an hour. So I'm going to start off with this idea that I mentioned, that the memory is actually implementing a truth table, right? We can use a memory to implement a truth table. And in this case here, the memory, I would say, is a ROM. So the ROM, read-only memory, you just program it once and then that's it. But what happens if this is a RAM? Okay, what happens if this is a RAM? Yeah, then there's no difference, right? It's just an address. You put in the address, you get the data. But the interesting thing about the RAM is you can rewrite the RAM, right? You can write new data into the memory boxes in here, which means to say, if I implement combinational logic with a RAM, I open up myself to the possibility of what I call programmable logic, meaning I now have the option of changing the combinational logic in my circuit just by rewriting the RAM, the contents of the RAM. Why? Because remember, what we said is the RAM can implement combinational logic, right? It can implement, any function. Let's say you want to put in an adder. Like if you want to implement an adder, right? So if you've got an 8-bit address, for instance, you've got 8 bits of address. So you can consider this is a 4-bit adder. Okay, the first, the LSB, the MSB is the first 4 bits, and the LSB is the sequence bits is the next 4 bits. Right? So if I have address 0, so you can interpret it as the first input is 0000, the second input to the adder is 0000. So the output, the data that you must send out will be 0, right? Because 0 plus 0 is 0. Then if you have 0001, 0001, then the data that you send out also is 0001, right? Here you can set this address, okay? If you were to go to address like this, 0010, this is equivalent to saying I add the number 0, 4-bit number 0 with a 4-bit number 2. So the result will be 0010. And then furthermore, I can have the address to be, let's say, 0001 and then 0010. So this is equivalent to saying I'm adding the 4-bit number 1 with the 4-bit number 2. So I get, so if you look at it like this, you can say, oh, all of a sudden, depending on how I interpret the address, I can program these values into this address, and then this RAM will now implement an adder. Okay, you implement an adder. And if I reprogram it, I say I want this to be a subtraction, right? So 000 minus 0001. So it's 2 complements is 1110. So you can program this like that. And 0 minus 2 is, this will be 1101. And this is 1 minus 2 is again 1110. So all of a sudden, if I reprogram my RAM with these values here, this adder all of a sudden becomes a subtractor, right? And again, the idea is I can do this in real time, right? Because I can do this while my circuit is running. So the interpretation that a memory can actually implement a circuit opens us up to the possibility of changing the logic function or the computation of the mode of that particular state in our circuit. And this is where we get this idea of programmable logic, right? So here you may actually hear the term, the RAM is actually functioning like a lookup table. Why? Because you are putting in the address, which is the inputs as, and you're looking up the value of the output, which is the data. Okay, that's why it's called the lookup table. And this is exactly one of the ways how FPGAs can be programmed, because you are not exactly kind of changing gates and all that. You are just programming lookup tables in an FPGA to implement logic. And here's where it gets really interesting, right? Because now if I tell you that I can actually put the memory and I can program the logic, this can be a RAM. This can be RAM. This can be a RAM. And this can be a RAM. Okay, which means that I have some way of selecting the mode, which tells me which computational operation I'm running. And I can use a RAM to actually program the computational operation. And if I find that I don't really like it, or it's not the best way, or I want to change the function of my circuit, I can straight away go in and reprogram the RAM, and suddenly it will perform a different function. So I can change the computational operation at the particular mode by reprogramming the lookup table. And this is the idea of what you have heard in maybe processor circles as microcode. Microcode is nothing else but you are implementing the combinational logic, the processing work as a lookup table using memory so that you have the flexibility to kind of reprogram things. And why would you want this flexibility? Well, one would be actually in the debugging and the testing stage. Like you're not quite sure the design meets all the specifications. It's a very complex set of requirements. So you can implement the desired logic as a microcode, test it out in real circuits, and then if it doesn't work, you can kind of change it slightly, and you don't actually have to build a new chip. So this is one reason why we might want a solution like this. The second will be more like programmable logic. You just want to make one type of general purpose chip, and then that chip can actually be used for many different functions, right? Because if I were to build one chip specifically to implement one particular state transition diagram, let's say that state transition diagram is controlling a washing machine, operation of washing machine. Well, guess what? That chip I can only sell to washing machine manufacturers, right? And then I'm very limited number of chips I can sell. It really depends on how many products. But if somehow I can kind of implement different state transition diagrams, different state transition combinations, I can sell more chips because these chips could be used in different cars and all that, right? So that's the idea of FPGAs. FPGAs, you actually can sell many more of them because you can actually program them. What you're doing is you're actually specifying a different lookup table, different combination logic function up to what you want, okay, in order to perform different types of computation, right? So that's why FPGAs are a good market because they don't just sell in one particular domain. They can sell in any kind of application because of the programmability. But I'd like to broaden your thoughts a little bit more, right? So we've talked about the programmability and how you could use that to kind of implement different computational operations in the mode that is in the data path. But then you realize that even the selection of the mode is a combination logic followed by flip-flop. Therefore, I can also program this part here. I can also implement this part here as memories, as lookup table. And if I do that, all of a sudden you don't need multiplexers and all that. You can actually just pop kind of a RAM here, right? And then this RAM is feeding the flip-flops. And just by changing the values of the RAM, I can basically implement different state transition diagrams. And this is the key point. Don't miss this point. So is this idea that, okay, since I can interpret a state machine as basically a bunch of flip-flops, okay, a bunch of holding the current mode, the current state, and all I need to do is I need to design a combinational logic. Okay, I need to design a combinational logic. Okay, and I'm going to just color this different color. I'm going to use this. I need to design a combinational logic so that the combination logic will update the next state or the next mode into the flip-flops. Therefore, the flip-flops, the next clock cycle will update the next mode, right? And really what we're doing is we are actually telling this circuit, specifying for this circuit, how will it transition between the different states? Would it go first from this state, then goes to this state, then maybe from this state, you want to go back to this state, and then from this state, you will go back to this state, and from this state, maybe you will go back to this state. This is a particular evolution, a particular sequence of states of modes, right? And this sequence of states of modes is basically, if you're in this state, right, if these values are holding a certain state, these values will be fed back into the RAM, into the address as an input. This RAM will decide, okay, go to this next state, right? Then it will load this next state value here, And when you want to decide the next state, these values will go back into the RAM as part of the address because that's the input, and you can decide to go into this state and so on, right? So if I were to change the programming of the RAM, I can implement a different trajectory of states. Basically, I can actually do the opposite. I can actually start from this state going to maybe this state, going to this state, going to this state, right? So all of a sudden, it opens up this concept that, hey, not just this idea of lookup tables, not just I can implement changes or be very flexible with the type of computation I want to do, I can also reprogram the sequence of state transitions. That means I can implement a totally different state transition machine, a state machine, right? A state machine is nothing else but saying a sequence of modes, a sequence of states I'm operating, right? But I can change the order of the states, right? I can also change the encoding of the states, right? So if you interpret putting a lookup table feeding a flip-flop, all of a sudden you have a programmable machine, right? Programmable in what sense? In the sense that the modes, the sequence of modes in which you will perform the computation can be changed just by changing the implementation of the state transition, right? And that is just by uploading or updating the lookup table, the RAM. And not just the sequence of modes can be changed, the actual computations that you do also can be changed if you implement it with lookup table, okay? And I'm now going to expand your concept of this programmable machine. So as mentioned, okay, yeah, this is a lookup table, it's programmable, okay. That means I can change the logic. And we talked about this kind of general machine, okay. Okay. Now we're talking about programmable state machines because not just the computation, but the sequence of instructions or the sequence of states can also be updated. And that's here. And if you really think carefully about this, now I said we can replace this with a RAM. We can replace this with a RAM, just like this. And basically, the RAM is actually specifying what will be the next mode, what will be the next mode, what will be the next mode, right? And of course, we said the RAM will take in some inputs, right? The inputs will be here. That will be the address, but the address will have to take some pins out of the current state and some pins from the inputs. Guess what? If you look at this, and if you're starting to move sequentially down the RAM, this looks suspiciously like a microprocessor, right? It looks suspiciously like a microprocessor. How? The RAM here is your instruction memory. So when you write a code, you write a code in C++, you press the compile button, it will compile into an intermediate code, and then the intermediate code will run an assembler and translate it into machine instructions. What is machine instructions? Just a sequence of binary ones and zeros that are stored in instruction memory. Guess what? Each machine instruction is basically stating the next state, and the next state is actually selecting the mode of operation. So a processor is nothing else but a flexible state machine whereby you code the next state in an instruction memory, and that instruction memory is implementing a lookup table that is selecting which mode to operate, right? Which mode. Okay, so what do I mean by mode? Well, that's your instruction. Your instruction is your mode is actually, am I doing an addition operation? Am I doing a shift operation? Am I fetching data from a RAM, right? So all these are operations of a microprocessor, but they're actually logical operations, computations, right? So a microprocessor now, I hope you understand, is nothing else but a programmable state machine. If you encode one particular state transition, then it's not programmable. It's a fixed state machine. But what makes a microprocessor flexible is because you can implement different kinds of state machines by writing different instructions, different sequence of code. That's your program. A program is nothing else but a sequence of instructions. And a sequence of instruction is nothing else but a sequence of modes and the data to operate on it. And a sequence of modes is nothing else but a sequence of states. Therefore, I hope by now you can get this concept and you can understand that if I give you a program in a microprocessor, you can draw a state transition diagram, or alternatively, you can draw an algorithmic state machine. And you can also figure out like this particular set of instructions or this particular program, I can actually implement it in hardware. If I just wanted to build a state machine out of it, I can, right? Because it's this idea that that state machine is actually your RAM. Your RAM is actually implementing a lookup table, right? The instructions are actually the lookup table, right? So the assembly instructions ones and zeros, that's literally the lookup table, right? So what's the input? The input's the program counter going to it. The program counter is nothing else but saying what is my current mode and what are my other inputs, and the other inputs would be things like where to fetch the data and things like that, right? But this is the idea that now you can understand microprocessor are an extreme form of programmable state machine, and this is just taking to its extreme interpretation, this idea that logic, combinational logic, can be represented, can be implemented in a memory. Okay, so you see two places where this is implemented. You see in the few programmable gate arrays, the actual computational task itself is implemented as a lookup table in memory. That's why your FPGA is full of static RAM, right? That you don't really find that many logic gates in an FPGA. It's full of static RAM. Why? Because each static RAM, sometimes they call it a lookup table or LUTs, as they like to say, or C loads or something like that. That's nothing else but a very, very small memory element, okay, with just a few address bits and a few data bits out, and that can actually implement any of these computational blocks to do computational on the data path. And in the microprocessor, the extreme form is the modes are actually programmable. Why? Because you're using the instruction memory to figure out the next state, and that next state is nothing else but your program instruction, your assembly instructions. Okay. At this point, any questions? Okay, if there are no questions at this point, there's one more paradigm of programmability that you will see over and over again, and this is programmable connections. Okay, so here, so far we've been talking about programmable logic. That is logic that can be changed. So what do I mean by logic? And or not gates, any kind of digital implementation where you have a truth table, inputs mapped to some outputs, binary inputs mapped to binary outputs. That's logic, programmable logic. Okay, but there's another paradigm of programmability, which is programmable connections. And before we start this, I have to really kind of firm up the concept of what we call a switch, right? So you should understand what a switch is. And let me talk a little bit more about what a switch is. Okay. Okay. Okay, so before I talk about what a switch is, then let me first kind of maybe describe a bit the big idea behind programmable connections. So let's say I have some fixed hardware function. This hardware function is implemented in AND or NOT gates and is doing some computation. It could be an adder or something like that, right? But I want you to just think about it as some group of gates, and right now I'm just going to represent it by an AND gate, right? Okay. I have a bunch of inputs coming from my coming into my chip. Okay, maybe I have 4 inputs coming into my chip. Okay, so maybe I want to check, and maybe perhaps, for example, these 4 inputs are actually coming from 4 different types of sensors, and I want to find I will do some kind of further computation if 2 of them are logic 1, right? So maybe I have to decide. I've only got this AND gate, and somehow maybe this AND gate I might need to share or to reuse it, right? So the idea is that, if for instance I have some mechanism where I can connect these connections like that, then okay, this AND gate all of a sudden can perform the computation on these 2 inputs. But if I want a little more programmability, I don't really want to hard code this. I may want an option where I can actually change the connection in such a way that I can connect it this way, right? Then all of a sudden I can implement a different function, right? Because it is the logic function is not changed, but the inputs over which they operate are changing, okay? So in the programmable state machine and the lookup table way of thinking, the way you provide flexibility at the input is you allow yourself to load the input into a memory, right? So that is your data memory or your registers, right? So if you're under the paradigm of memories, right? I'm using memories lookup tables. I have the flexibility to reconfigure inputs from one versus input for another, right? Because I can reconfigure the calculation, but I can also reconfigure what are the input signals that I'm performing the calculation on. So in the lookup table paradigm, the inputs can be flexibly allocated just by allowing you to load it into memory. So it's this idea that maybe I have a whole bunch of inputs. Okay, I can actually have all the inputs coming in here. Then I can have a multiplexer. Can have a multiplexer like this. And the multiplexer allows me to choose which of these inputs I'm going to store in here, and then this mode selector will allow me to then operate on their inputs. So the lookup table version, the idea is always you are loading the different state configurations into the instruction memory, and the data part itself, choosing the inputs you load into the data memory. So this is called a load and store architecture, because what you end up doing is you end up loading memory with a lot of different inputs, or it could be the output could go back into this in this storage here, so that it can be reused or selected flexibly to go into any of these ideas. So it's a load store because you load here into the memory, and then you store into this memory, and then you load it out into the compute units to do the processing. Okay, whereas for the programmable connections approach, the logic is typically fixed, and you must have some way where you can flexibly reconfigure so that you can connect different pins into this, right? And I think the issue is just that how do you do that? And that's where the switch comes in. A switch is this special circuit where you have the ability to control, okay, you have the ability to control the mapping of inputs to outputs. Okay, what do I mean by that? So this is an example of a 4 to 4 switch. Okay, that means I have 4 inputs that could be mapped to 4 outputs. And so what I can end up doing is I can go ahead and hardwire, directly connect my circuit resource into a switch like that. And supposing I want to actually connect this first input to this first one, this second input to the second one. So the switch internally will allow me to create a connection directly across here like that in order to connect that up together, okay? But when I do this like this, it is now no longer possible for me to connect this input to this output, right? I only have 4 inputs in, and I've got 4 outputs, and these 4 inputs must be assigned uniquely to these 4 outputs. That's the role of the switch. So at any one time, I can actually assign something like that, or assign something like that, or assign something like that. Or I can change this assignment and then push it down here, and then this one has to, this assignment goes like that, okay? So the way the switch works is it allows you to change the mapping of one input to whichever output pin, okay? And this is a kind of a shortcut trick in order for you to have some flexibility. Why? Why? Because if you think about this, let's say I only have this resource, right? And I need to actually do the AND of this signal with this signal, then this signal with this signal, and then this signal with this signal, this signal with this signal, this signal with this signal. So there's 1, 2, 3. 4, 5, 6. There's 6 combinations of ANDs, right? So if I don't have this programmable switch, I need to build 6 AND gates. I need to replicate that same resource 6 times to do this. But if I've only got one resource, right, and I want to kind of save, right, on the resource, the hardware here, I can actually say, okay, I can actually take turns to use this same resource. And what do I do is, I program the switch, right? So in the first time instance, I program the first 2 connections to go up like that. So I get the result here, and then this result, I can store it. Then the second time instance, I program the switch like that to take the end of these 2. The third time instance, I program the switch like that to take the end of these 2. The fourth time instance, I take the switch to do like that. The fifth time instance, I take the switch to do this. And the sixth time instance, I take the switch to do this, right? So you can see that with these programmable connections, I actually have a paradigm. I'm able to actually reuse the same computational architecture. I can reuse it to do computations on different inputs, but I spread it out in time rather than I spread it out in space. Okay. If you were to spread it out in space, that would require more hardware, right? So because you have to build 6 of these, something like this. Right? And then you have to connect this one to the first one, this one to the second one, this one to the first one, this one to the third signal, this one to the first one, this one to the fourth signal, and so on, right? So this idea of having programmable connections allows me to compress my implementation circuit because it allows me in a way to reuse the same computational blocks, but changing the inputs to the system. Okay, so it's a form of kind of like space saving, right? And if you go back and think about the programmable state machines that from the lookup table kind of paradigm, this is exactly what the lookup table is doing as well, right? So if you want to implement 3 different state machines, right, rather than having the hardware to implement 3 different state transition diagrams, I have one flexible one, and I load program 1, I run that state transition diagram on all the inputs for program 1, then I remove program 1 and then load program 2, and I run a different state transition diagram on that, I compute it, then I remove program 2, I run program 3, I can run the third state transition diagram, right? So this idea of programmability not just gives you the flexibility to change a circuit, so that's kind of helpful when you're not quite sure, you want to test things out. In case there was a mistake, you can make changes, but it's also a paradigm that allows you to save on computational resources, right? You don't have to have a dedicated circuit for only one task and one set of inputs. You can reuse that task, the circuit doing that task, for different inputs in different sequences because of the programmability. So you can think about programmability as allowing you reuse of hardware by sacrificing time. That means this same hardware, you are using it for different configuration of inputs at time 1, time 2, time 3, time 4. Whereas if you were to replicate this same hardware for each of those cases you want, you have 6 times more hardware or 8 times more hardware, but you get your results all in one time epoch, right? But if you're kind of reusing that hardware, you have to kind of reconfigure or reconnect it, change it, but you take longer time, right? So programmability allows you to trade off resources or space with time, okay? So that's an interesting concept, a very important concept too, because the opposite can happen, right? If you find that your circuit is having some kind of bottleneck that you need to wait to compute things, you can always save time. That means you reduce the time by adding more resources, space. So there is a trade-off between the two. Okay. So then this is how you can actually improve and increase computational speed. You have to have another circuit resource, another computational unit, or more than one. You can have more than that to run computations in parallel. This is the idea of parallelization. That is, you're trading off time. You're trying to reduce the time by allowing computations to run, similar computations to run on replicated instances of your compute unit. Okay, so this is why that paradigm is interesting and important. Okay, so I've talked about the switch, the programmable connections. I don't want you to feel too, that is too difficult, right? I'll just show you how you could possibly implement a switch very easily, right? what you can do is basically you can have a 4-input multiplexer here, and you just have 4 of these. Okay, this is one way to implement a switch. It's not the best way. Okay, so we're not talking about optimal, but I just want to show you that it's entirely possible to implement a switch using just logic functions, right? So if you have 4 multiplexers like this, okay, so these 4 inputs are these 4 inputs, right? And this output is the output to the first one. This one 4 inputs are these 4 inputs. This is the output to the second output, third and fourth, right? So all of a sudden you actually have all of these, and you have the selection bits, and these selection bits can actually go into uh, a a combinational circuit, and this combinational circuit is basically what they call a decoder lah, or a scheduler, right? Because this combinational circuit, what it's doing is just saying which input to map to the first output, which input to map to the second output, which input to map to the third output, which input to map to the fourth output, right? So if you want to program this, you just need to program this scheduler, right? And this scheduler again can be a RAM, right? That's how to make it flexible. Or you can think about it in terms of multiplexers and choices, lah. And then it depends on how you are storing the program. So I just want you to see that this switch is not some amazing circuit. It can literally be just a simple combinational circuit, just like this, okay? But this idea of programmable connections is very powerful because it is a second paradigm of allowing you flexibility in your circuits, okay? And a few programmable gate array is basically the best example of a programmable system because it incorporates both memory-based programmability, lookup tables, as well as connection-based programmability. Okay, so an FPGA has both the lookup table-based programmability for logic and connection-based programmability. So that's why the FPGA is so flexible, because it allows you both types of programmability, and it's up to you as a designer to figure out which sort of programmability you want to use. But I'm kind of showing you this and teaching you this because I want you to have this concept, right? This concept of programmability. It's not just writing code, right? The simplest is actually you're just filling up a memory element, and that memory element is implementing a combinational logic. But if you take that a step further, based on your understanding of selecting modes and performing calculations within the mode, you can see that you can program the different calculations, okay? And you can also program the sequence of states or the state transition of your system, which is nothing else but instructions in a programmable system, okay? You can also program the connections of the inputs to the computational units, or even to the state transition itself, using programmable connections, and that's typically implemented by a switch. And this switch program, or how it's connected, is actually can actually be implemented in a RAM. So again, this RAM would be saying which address, what 4 bits will be set here. So in this case, you just need to store 4 bits, right? But if you want a programmable RAM, that is, you want your switch to be able to change configurations, you can actually put in an address here, and depending on the address, that address will actually give you which combination of connections you want to enable in the switch, right? So is this paradigm? Yes, 2 paradigms of programmability. One is the programmability is in the memory element, is implementing a lookup table or a truth table. And the second is the programmability in terms of connections, which is just merely allowing you to kind of swap connections to a particular fixed circuit element, right? But again, as I mentioned to you, that in an FPGA, this is not a fixed circuit element. This, in its most flexible form, is a lookup table, like that. Okay, right. Any questions at this point? This is a pretty deep concept, but I hope you can pick it up. Any questions at this point? Okay, if there are no questions, then looks like we maybe might be on time to finish within the hour. Let you all off early, and you can either take a break because it's been probably a long week, you're probably tired, or you can just work on the assignments or something like that. The final thing I want to actually kind of go on is this idea of nested state transition diagrams or nested state machines. Okay. We've not necessarily talked about state machines too much because that's very fundamental, but let me suppose I have a state transition diagram, which is implementing a state machine in this fashion. So let me just kind of draw these arrows a little bit larger. Okay, format shape. I can go for this and then the end arrow size for a big one. Okay. Okay, if I show you a state transition diagram like this, right? And I just call these states A, B, C, and D. So in practice, I would discourage you from calling them A, B, C, D because they're not descriptive, right? You should call a state by, as best as possible, by the mode of operation which is doing. So like, for example, each state could be an instruction in the microprocessor, like add, load from memory, subtract, shift left or shift right, or divide, right? Okay, but for just for the purpose of instruction, for simplicity, I'll just call it A, B, C, D. If you look at this way, this state transition is actually saying on the first clock, perhaps I start with state A, then at the next clock cycle, I go to state B, and what happens in the clock cycle after that? Well, it's a bit confusing, right? Because you got two possible routes. You can go to C or D. So when you have two possible routes, that tells me that this transition must happen dependent on some input. Okay, input. Okay. So you would have maybe input condition 0, then you will go to state D, or input condition 1, you can go to state C. And then from D, at the next clock cycle, it goes to A. Okay. So most people from undergraduate, they forget that if you don't label the state transition with an input, it will transition to the next state automatically at the clock age. Okay. So it's like saying that I'm writing a program, but I'm just kind of, I'm not waiting for the results to compute. I'm just going to move from mode to mode to mode to mode, right? That could be okay in some cases, but you have to be aware of that, right? Because in general, most situations you will require some kind of input condition whereby if that condition is not fulfilled, you will continue processing in that state. Okay, does that make sense to you? What I'm just saying? I'm saying in most cases, most useful state transition tend to be of the form where if the processing or the computation isn't finished, you continue to remain in the state at subsequent clock cycles. Okay, so when the input is 0, you remain in the state. But when there's suddenly some kind of condition, okay, I'll say when the condition is 1 is true, then you transition to the next mode. Okay. Most useful and useful state transitions like that, because again, like for example, you might be used to RISC microprocessors, and RISC microprocessors, one of the defining features is every instruction will execute in one clock cycle. But when you go to more complex operations, like let's say you have a multiplication operation or division operation, you will find that sometimes the division or the multiplication doesn't complete in one clock cycle. It might not even complete in two, right? So if you draw a state transition diagram without a condition of going forward, you know, it's like you're not even finished your multiplication and then you want to do the next operation, the addition, right? So most likely I like to encourage you to actually think about state transition as the default is if some condition for completing the calculation or in that mode is not done, that condition has to be set to 0 and you still retain in that mode, right? You take how many clock cycles, and when you want to transition to the next mode, a condition has to be fulfilled, right? And so here is also the same condition, except that here maybe you have condition 1 and you have condition 2. It doesn't have to be a binary condition, it could be a multi-bit condition, right? So if you have condition 0, you might actually still retain or remain in that particular state. Okay, so the most general state transitions are something like this. Okay, in general they stay in that mode or they stay in that state until the computation is done, and that is actually signaled by some kind of condition signal. So you will transition to a different mode, a different state when that condition is done. Okay, and in order to calculate this condition, okay, in this condition, you can actually have another state machine that is calculating this condition. Okay. And what would be the simplest example? The simplest example could be something like a timer function. This is my favorite example how to showcase this, where basically I can have a timer, okay, and timer I can implement a state transition diagram, and that state transition diagram is nothing else but a counter. So counter, there's no conditions, right? So let's say I count 3 clock cycles. In this case, I count 3 clock cycles. Okay, this is maybe your clock cycles are 1 nanosecond apart. So this is 1 nanosecond has elapsed, 2 nanoseconds has elapsed, seconds has elapsed, and maybe you have one more state which you call as the waiting state. And again here, I'm reusing the idea that if there is a condition pause is 1, I pause, I stay in the waiting state. If pause is 0, I start counting. And I will transition every clock cycle, 1 nanosecond, 2 nanosecond, 3 nanosecond. Okay. So why am I showing you this? I could actually implement the condition for moving from this state to this state based on some output condition, and that output condition could be output within this state. So you can actually say condition, and you actually can have 0, and condition equals 0. Okay. So when you're in this state, let's say you call this state wait timer. Okay. So when you enter this state, okay, the fact that you enter this state, you will set the pause signal to 0, and then this state machine will start activating and computing, and once it reaches the 3 nanosecond condition, it will output the condition 1, and then you can actually jump to the next state. So you can actually implement state machines within a state, right? That's nothing else but at a particular mode, you can actually have a situation where you don't allow the mode to change until some state, a second state machine has completed. And the simplest example of this would be a timer function. So this is how timer functions are implemented, right? So like you have like a timer interrupt, or you have a countdown clock. That's nothing else that can be interpreted as having another state machine. Okay, this is a nested state machine. The state machine is actually a counter, the simplest possible one. And when you enter the state, you enable this state machine. And once this state machine has completed, it has some condition which then allows you to jump to the next mode. And the counter would be the simplest example, but I hope you can also see that it doesn't have to be a counter, right? You can enter this state and it could allow you to have sub modes. So the simplest way, another way to think about this would be these states could be your major modes, and within, when you're operating within a mode, you could have sub modes or nested modes that, you know, you can actually do certain functions there. And why am I saying this is powerful? Because number one, if you actually have nested state machines like this, it really makes the design process that much simpler, because you know that this single state machine can be implemented as a set of flip-flops with combinational logic. And this second state machine can be implemented with a separate set of flip-flops and combinational logic. And if you don't have this nesting, you will have so many other states, because you will have a wait timer state with 1 nanosecond condition, wait timer state with 2 nanosecond condition, wait timer state with 3 nanosecond condition, and so on, right? So if without this idea of nested states, your state transition machine could grow very big with so many states, and it becomes very difficult for you to track and to ensure correctness, right? Whereas if you actually break it up into subparts like that, you know that there's separate state transition machines. You can test these state transitions separately. That means this, because this is a separate flip-flop and circuits, you can test this separately from this state transition. And then you can test the interaction, this separately from this one, and you can test the interaction. Whereas if you were to combine this as a wait timer 1 nanosecond, wait timer 2 nanosecond, wait timer 3 nanosecond, it's a little bit more difficult for you to test this only a part of this whole state machine, right? So these are just some of the examples, and a way for you to think about how to simplify your reasoning. This is what I call nested state machines. Okay. All right, I've pretty much come to the end of what I want to cover for tonight. As I mentioned, this is starting to get into kind of just advanced techniques. It's just basically enlarging your repertoire of tricks you can use in your circuit design process. I hope you've gotten started with designing the complete circuit for this password lock system. And I hope by now you've also started looking at the problem-based assignment, that is the SDRAM controller. You can start applying all these tricks and techniques to solve that problem. There's going to be one more assignment question. I've not released that yet, and so there's only a total of 3 kind of assignments. That's the heavy one, the SDRAM one with the FPGA implementation, and 2 lighter ones, one of which is this passcode circuit implementation. Because we've covered this in the class, some aspects of the discussion, so this is more of like helping you to formalize the concept, understand, and you can explore how to use some of these tricks and some of this way of thinking about circuit design that I've shared in this will be the 3rd session now. Okay, so I'm going to go around the table, maybe wait a little bit longer if there's any question on the material we've covered today, or if there's any question on any of the material you've read in the textbooks, or there's any questions on any of the material we've covered in the past. So just feel free to ask. Or even if it's not related to the material, but it's related to digital circuit design, yeah, feel free to ask. So just go around the table, see if there's any questions. Yeah.
Regarding the assignment for door lock or like other assignments, is there a rubrics or documentations like what that assignment is going to cover?
I'm pending to set up the submission for the passcode one. I'll probably do it in this week. So sorry about the delay there. You can actually refer to the assignment plus EA grading rubric is actually the same. It's over here. This is how I will typically grade all your assignments, because they're design assignments, right? The design assignments, they are all the same lah, typically. First, I'll give you some grades for design specification. Second, I'll give you some grades for the verification plan. So it's following the list that I mentioned. Then I'll give you some grades for how you describe the data path or the interfacing part, right? So that corresponds to this part of the circuit. Okay. I will give you some marks for the control path. That is typically the state transition diagram, the state machine, the state transition diagram, the mode selection, this part here. Okay, so I separate this out because it's just trying to promote this practice that you understand which is the control path, which is nothing else but saying the selection of modes, and which is the data path, which is nothing else but saying the computations. If you can usually separate out your design this way, it's more readable, it's more helpful and all that. But if you don't, I'll be able to pick that up, lah. No problem. Why? Because frankly speaking, if this is a milling machine, this part is the control path and this part is the data path usually. Yeah, that's how I'll be able to pick it up lah, in terms of the rubric. So you get some marks for the design of the control path. Then there's a design of the test bench. So this is the verification plan. This is planning what you are actually going to test the output. This one, I'm giving you marks for the actual RTL code and setting up the test bench and connecting it up to the Verilog RTL and then running the simulation. So this is more of the practical aspect of just doing the verification and showing that, yeah, really, I get my design actually implements what I said it would implement. It follows the verification plan, it follows the design specification. So this part is that. And then the last one is the timing analysis. This is more of kind of looking at the correctness of your circuit, right? So the correctness of the circuit, I would do a basic grading on under these two rubrics, right? So I'll just say, okay, if you meet certain things, but sometimes when you're starting to design these things, you will find that the most difficult errors are actually the timing errors. You might actually get the correct output sequence, but maybe you're off by one clock cycle and all that. This is where this comes in, or you've forgotten to factor in, you forgotten to mention the clock cycle, and then you forgot, it's some of the problems actually that will come up, especially like the SDRAM one. That's a really, really good example. You have to wait a specific duration of time, not a specific number of clock cycles, right? It's a specific duration of time, right? Because the circuit you're interfacing with has this kind of time limitation, there's a certain delay. So this timing analysis part is actually catching you to see, did you actually pay attention to the specification of the problem, to the requirements, where is there any kind of specification in terms of time, and how do you relate the specification in terms of time to your system clock, right? Because you have to understand that your state machines are actually being run on a system clock. What do I mean by that? These flip-flops are actually updated at every clock period. So you must define what is your clock period. Is it a 1 megahertz, a 10 megahertz, a 100 megahertz, and all that? And the default is that you are evaluating one possible state transition every clock cycle. So that's why I'm asking you to look at this condition way of thinking it, because you will tend to forget, especially if you've not done a lot of design before, and you will just start drawing these kind of transition lines without condition. And what that implies is actually this thing will be updated every clock cycle. So let's say you're running on a 1 gigahertz clock, you forget that this is actually running on a 1 gigahertz clock. And I think I really saw that many of you missed that, right? You were thinking that, okay, after this passcode, the buttons will be pressed at every clock cycle, right? And that's not true. If you're running on a 1 megahertz clock, you'll be actually waiting in the first button state for at least 1 million cycles before the next button comes in, right? Because people don't press buttons in less than a second, that kind of thing, right? So this timing analysis part, I'm actually assessing you on your awareness of any timing constraints and how you actually implement that timing constraint or that timing properties, taking into account your system clock is actually running at some kind of frequency, right? Does that make sense? And also looking at your I/O lah, whether you have respected the max delay, the mean delay, and whether the I/Os are changing at the right time, and so on. Okay, I hope that answered the question, Sheng Li. Okay, great. Okay, more questions. Okay, going once, going twice. All right, if there's no more questions, then thanks for your attention. You can always get in touch with me if you have further questions after thinking about this material. It's recorded. I'm going to upload it to the website, the ULearnX, so you can always review this material. Please get started on the assignments. Please don't wait till the last minute. And if you have any difficulties, especially in reading the data sheet for the ST-RAM, please raise that early. We can actually discuss in our virtual sessions. But it's not my intention to have too many virtual sessions. As I've told many of you, I try to limit it to at most about 5 sessions, 2 hours each. So we are roughly like halfway through. So if you need more sessions, we can do it, but there's actually no necessity for us to keep meeting on such a regular basis if there's no questions. Okay, so I'm going to stop the recording now.